All right, welcome everybody. So first of all, thank you for coming. We're really excited to host the first Rust Meetup in Kitchener-Waterloo. Hopefully this is the first of many meetups to come. I want to start by thanking Sortable, who allowed us to use this room, and thank you to Mark, who actually put all of this together and had the initiative to put together a Rust Meetup here. So thank you, Mark. Really, none of this would have even happened had Mark not contacted me and started setting all this up and then done all of the work to get all of this put together. So thank you very much. Let's get started with the talk. So I'm Sunjay Varma. I've been programming in Rust for about 2 years, and I've written quite a few projects in Rust, and I've even contributed bits to the Rust compiler. Today I'm going to give you what I hope is a practical introduction to the Rust language. So there's a link to my slides at the bottom of the screen if you'd like to follow along on your own devices. Please go to that link now if you do. I'm going to start by telling you a bit about the Rust programming language and why you want to use it. Then, for most of the talk, I'm going to give you a practical introduction to the Rust programming language. And I'm going to try to take you through an example of implementing a small program that's going to play the game tic-tac-toe. After that, I'm briefly going to touch on a few of Rust's most advanced features. The great thing about Rust is that you can very productively write a lot of code without even using the advanced features I'm about to talk about. They're the kinds of features that don't really need to be used all the time, but when the situation comes up where they come in handy, you're really glad that Rust supports them. This is great because it means you can learn Rust a little at a time without having to understand all of it at once. Finally, I'm going to conclude with some remarks about the language and give you some resources to learn more. So let's start by briefly going over what the Rust programming language is and why you want to use it in the first place. If I was given one sentence to describe the Rust programming language, this is probably what I'd say. Rust is a safe, productive, high-performance, and low-level programming language. That's a big sentence, so let me break it down. Rust is safe. So Rust has automatic memory management without garbage collection. That means that instead of having to manage memory directly and then be responsible for cleaning it up afterwards, Rust does all of this work for you. The remarkable thing about this is that Rust does this without having a garbage collector. Most languages that do automatic memory management require having something that either runs with your program or stops it completely in the middle to free memory when it stops being used. This can impact the performance of your program a lot, and Rust is able to avoid this and guarantee safety because the Rust type system provides enough information for the compiler to figure out exactly when a value should be deleted. The mechanisms for this are called ownership and borrowing, and I'll discuss them later in the talk. The amazing thing about ownership and borrowing is that Rust is able to make some pretty amazing guarantees about your program. Any Rust program that successfully compiles is guaranteed to be memory safe and data erase free. That means that a whole bunch of common memory errors are completely eliminated. You get rid of use after freeze, double freeze, dangling pointers, and so many other things. Safety means that a Rust program will never seg fault. If you use multiple threads, Rust catches a lot of common concurrency problems that can be really hard to debug, even before your program is run. So Rust is productive. You can actually start writing production-ready code in Rust today. And the reason I'm so confident about this is because all of these companies already do that. All of these companies know that Rust is ready to be used in production in their apps. And this is from the Friends of Rust page on the Rust website. I actually highly recommend that you go to that URL because you can see exactly what each of these companies is using Rust for. So Rust is designed to be a productive language. You're actually meant to write code in it and use it for things beyond small personal projects and research. Like, while there are some cutting-edge features in Rust, a lot of Rust is based on old, established techniques which have already proven to be effective in other languages and throughout the field. When you use Rust's type system, you end up describing your program in a way that gives the compiler a lot of power to check if it's correct. Often, just getting your code to compile means that you've already avoided a ton of potential bugs. You don't have to wait until your program is halfway finished to find out that you did something wrong. This is great because while you're writing code, but even better when you're trying to come back to it after some time. Knowing that the compiler has your back gives you a lot of confidence when it's time to refactor or fix your bugs, because you know that the compiler will do all the same checks every time. Rust is high performance. So just like low-level languages like C or C++, Rust gives you a lot of control over how your program is represented and run. You get to choose the trade-offs you make between efficiency and memory representation. Rust does the majority of its safety checks, correctness checks, and memory management decisions at compile time, so there's no runtime impact for writing safe, correct code. As I mentioned before, Rust does automatic memory management without garbage collection. All of the decisions about allocating and freeing memory are made at compile time so that there's no impact on your code while it's running. And Rust borrows the excellent concept of zero-cost abstractions from C++, so that you get to write code that feels really high-level, but is as performant as if you'd written it in a lower-level language. So Rust is low-level. All of the amazing things I've mentioned so far wouldn't be complete without mentioning that Rust is a low-level language. And I put extra emphasis on this because Rust doesn't feel like a low-level language. Like, you don't spend hours debugging all kinds of crazy memory issues or concurrency bugs. And even though Rust supports advanced features, you don't need to deal with any of the overhead or with any extra overhead because of them. So Rust gives you complete control over your program without forcing you to take the entire responsibility to make sure that your program is correct. You might be wondering, though, if Rust supposedly gives me complete control, how can it also manage my memory for me and do so many other things by default? Well, it turns out that Rust has this concept of unsafe. This is a way for you to tell the compiler, hey, I know better. So probably a better word for this would be unchecked, because while you can do unsafe things with unsafe, most of the time you only use it when you have a specific low-level need that Rust safety guarantees conflict with. Unsafe lets you do inline assembly, raw pointer access, and all kinds of other things that you'd expect a low-level language to allow you to do. So what does all of this get you? It gets you a language that you can actually write code in and really enjoy without sacrificing power or performance. You get to write code with the powerful abstractions of a high-level language and the performance and control of a low-level language. There's a reason that Rust has been the most loved programming language for 3 years running on the Stack Overflow Developer Survey. Now, with all of that said, let's jump into some Rust. I want to give you a practical introduction to Rust and get you to the point where you could at least start to experiment with the language and write some programs. The way I'm going to do that is by getting us to go through writing certain parts of the game tic-tac-toe. As we go through it, we'll cover a lot of different aspects of the Rust language. Now, I'm not going to have time to go through the entire program with you, so I've actually prepared a fully commented version of the example and thoroughly commented it with descriptions of exactly what I did and the decisions that I made. So there's a link at the bottom of the slide to that if you want to check that out later. Now let's start by covering variables and functions. So Rust is a statically typed language. Statically typed means that every value in your program has a specific type known to the compiler at compile time. The way that Rust gives you all of the benefits that I described is by knowing a lot about your program through these types. Rust has a feature called type inference, which means that the Rust compiler can figure out most of your types for you. So even though it has types, you often don't even need to write them. Functions in Rust are one of the few places where you're required to put type annotations. This is actually great because it gives you a completely obvious way to know exactly which values a function expects just by looking at its type signature. In Rust, the syntax for annotating types on variables is the same as the syntax for annotating types in functions. you put the type after the name using a colon to separate the two. The return type is annotated after the function arguments using the arrow you see pointing to I32. This example also shows another aspect of Rust, which is that the last expression of the function is used as the return value from that function. So here you see that x and y are put on their own lines without a return keyword or a semicolon. That means that one or the other will be the result of the if statement, and then that will be returned from the function, since the if statement is the last expression in the function's body. Rust also has a return statement just like any other language, but it's typically reserved for cases where you want to return early from a function. And we'll talk about an example of doing that in a few minutes. The complete tic-tac-toe example that I mentioned that's fully commented has a couple of different places where we use return explicitly to exit a function early when we know that we definitely shouldn't go on. So here's some common Rust types that you should keep in mind throughout the rest of the talk. Now, we won't use the majority of them, so don't worry about memorizing any of them now, but it's good to know that they exist. So Rust has 5 unsigned integer types. The number after the letter U represents the number of bits in that type. So U32 is a 32-bit unsigned integer type. This same convention is used for all other types as well. There are 5 signed integer types. The types you see at the end, usize and isize, are a little special because they're used to index arrays and represent array lengths. Their representation depends on your platform and architecture. There are 2 floating point number types, a 32-bit floating point number and a 64-bit floating point number. To represent whether something's true or false, we have the bool type. To represent a Unicode character, we have the char type. And there are 2 string types, both with full Unicode support. The second string type you see there is a growable string type, and it's allocated on the heap. Rust has a unit type, which is kind of like Void in other languages, but not so much of a special case. And Rust also has special compound types, like option, which we'll discuss later, and tuples and fixed-sized arrays. These types can contain other types, like the ones I just mentioned. Again, don't worry if you're not familiar with all of this. I just wanted to show you that these things exist so that you know a little bit about them when they come up. Now, Rust could have all of the amazing features in the world, but if it didn't have great tools to match them, it would fail as a language. Like, it's really hard to use a language if building and running your code is difficult to do. Luckily, Rust has great tools in its ecosystem, including the excellent package manager and build tool called Cargo. We can start our tic-tac-toe application by using Cargo to create it and run it. To create a new project with Cargo, all we have to do is run the command cargo new and provide it with a project name. We can then run the command cargo run to compile and run our program. It's really that simple. Like, there's just 2 commands to get set up and get started. Now, we won't talk about tools very much after this, but you should know that Rust prides itself on having very easy to use and helpful tools that are easy to learn. Let's get back to the language. So we've covered variables and functions. So now let's move on to 2 very important features that we'll use to start our tic-tac-toe application, structs and enums. We need some way to represent the game board and the pieces that can go on it. Structs in Rust look something like this. You give the struct a name, and then with each field you specify the type after a colon. This is similar to what you saw with functions and with variables. These are a little different from the structs you might have seen in other languages because struct fields are private and there's no classes in Rust. The struct is going to be used to represent our tic-tac-toe board. Its first field is a 2-dimensional array of pieces because the tic-tac-toe board is 2-dimensional. This is the syntax for declaring the type of a fixed-sized array in Rust. We put a type name and then the size of the array after a semicolon. By nesting that syntax, we can get an array of arrays which we'll use to represent the rows of our board. The second field is used to store the piece whose turn it is to move. And the last field is where we store the winner of the game once the game is complete. The reason we store that is because it takes a couple of seconds, like it takes quite a bit of computation to compute the winner. And so we don't want to do that over and over again. And so we store it and only set it once. Option, which you see here mentioned a couple of times, lets us represent that tiles might be empty, like there might not be any piece there. And it also lets us represent that there's no winner in the game until the game ends. And we'll talk about that more in just a minute. Structs are how we represent a combination of different types that we always want to pass around and use together. Enums are how we represent having multiple possible alternatives for a value. Any tile on the board that has a piece can have either X or O, but never both. The game can end with either X winning, O winning, or neither winning in a tie, but only one of those can be the case at any given time. Enums are a natural way to represent these choices. And enums in Rust can actually be even more powerful than what we see here. Each variant can have different fields, so you can pass even more information depending on the situation. Option and result, which we'll see in the next slide, are excellent examples of enums that have fields. The complete tic-tac-toe example on GitHub uses this feature to provide more context about different errors that can occur when making a move. Now let's talk about two very important features in Rust, option and result. Rust uses these types instead of having a null value or having exceptions. If you've ever dealt with either of those extensively, you know that both null and exceptions have big drawbacks that can make them really frustrating to use. Rust takes all of that away with these two types. The first thing you should notice is that both option and result are just regular enums, like the ones we saw on the previous slide. Option is a type that represents the possibility of there being some value or no value. The sum variant of the option enum stores a field of some type t. Now don't be afraid of those angle brackets, they just mean that t can be any type. If there's no value, you use none. By using enums like this and not having a special null value, you always know exactly when you need to think about the possibility of some value being there. It's never a surprise. There's never a null pointer exception. Rust ensures that you don't forget to handle the case when you need to. Result is used for when an operation might fail. It has two variants, OK and error, which both have one field. If an operation is successful, you use OK to provide the completed value. If something goes wrong, you use error to provide an error value that tells you what happened. We'll look at an example of this on the next slide. Both of these situations that these types model are very common in pretty much all programs. And Rust gives you these types so it's easy to get it right whenever either situation comes up. So here's a function from our tic-tac-toe program that uses result. Now, just remember that there's a fully commented version of this function in the complete example that I linked to earlier. So I highly recommend you check that out. So this function takes a string of user input and attempts to convert it into a row and column index that it corresponds to on the board. The top right of this slide shows how we display the game board to the user. The columns are lettered A, B, C, and the rows are numbered 1, 2, 3. We want the user to enter something like 1C, and then we want to convert that into a position 0, 2, since 1 is the first row and C is the third row. Since the user could provide any input at all, this function has the possibility of failing. To model that, we use the result type as the return type of this function. You can read this function as parse move takes a string as its argument, and if it is successful, it returns a pair of unsigned integers. If it fails, it returns a type called invalid move. Invalid move is defined at the Invalid move is defined at the bottom and is similar to the struct you saw earlier. It's actually called a tuple struct, and it only has a single field for the invalid string that we want to tell the user about. So this function starts by checking if the length of the string is not equal to 2. If that's the case, we already know that this could never be a valid input, so we return right away. This is the first time we've seen the return keyword used explicitly, and it's really useful because we know that we want to return early from the function as soon as this error is found. Next, we see two match statements. Match statements are kind of like switch statements in other languages, but even more powerful. Each line in the match statement starts with a pattern, and if the pattern matches the rest of the line, and if the pattern matches, the rest of the line to the right of the arrow is returned. So in the first match statement, we're looking at three patterns for each possible string that can be provided as a row number. If any of them match, we return the correct row index and put that in the variable row. The variable call is similar, and it's set to the correct column index based on the letter provided in the input. Notice that we can use a vertical bar or pipe character to separate different patterns. If any of those match, the right side of the arrow is returned. So this lets us do what we also could have done with many if statements in just a few lines of code. Now the underscore in the first match statement matches anything at all, and we use that to return an error if the user provides anything other than exactly what we know is valid. In the second match statement, we see that we can actually create variables in patterns. If none of the above patterns match, the column letter that we're matching on will be put in a variable called invalid. Then this will be used to provide an even more specific error message to the user. So let me go back to the first match statement. So the underscore there matches any pattern, and we use that to return the entire string. But in the second match statement, we see that we can use variables in the match. And I just want to highlight this because this was just before the video got cut off. So what that second match statement does is it takes the character that we're matching on and it puts it in that variable invalid. And that lets us provide an even more specific error message to the user. Finally, if both match statements succeed, we return a successful result from the function using OK. This is that other variant of result that we use in case our computation is successful. Now, the key thing to note here in all of this is that we aren't throwing exceptions when we come across an error case. Errors don't have to be a special case in your language. Instead, we're considering an instance of a regular type called result, it's just a regular enum, and returning either a successful value or an appropriate error based on what happens. Just like with option, by using result, Rust allows you to be sure that you handle errors when you need to, and then you don't need to worry about them otherwise. You never have to be surprised about an exception. Modeling your program this way makes it really hard to accidentally forget a case that you should have accounted for. Now, let's spend a few minutes and talk about ownership and borrowing. These are two foundational features of Rust, and understanding them will help you see how the language is able to make such strong guarantees about things like memory safety and freedom from data races. Ownership allows us to know exactly when we can free a certain piece of memory. And there are three ownership rules. If you've ever used smart pointers in other languages, these rules will be familiar to you. The first rule is that each value in Rust has a variable that's called its owner. The second rule is that there can only be one owner at a time. And the third rule is that when the owner goes out of scope, the value will be dropped. Dropping a value is the same as freeing its memory or deleting it. And these three rules are at the core of the Rust programming language and how it works. Every variable you create owns its data, and then when that variable goes out of scope, the data that it owns is dropped. Since there's only one owner at a time, there's no complicated decisions that need to be made when we're determining if we can drop a variable. As soon as the owning variable goes out of scope, we drop its value. So this is how Rust manages your memory for you without needing a garbage collector at runtime. Now, if we could only ever hold on to a value in one variable at a time, we wouldn't be able to write a lot of useful programs. So this is where borrowing comes in handy. Borrowing allows us to temporarily use the data owned by another variable. This lets us pass a value to a function without moving the value and transferring ownership. And I'll show you what I mean by that. In this example, the string hello world is owned by the variable x. When we pass it into the function, its value is moved into that function because the second ownership rule says that there can only be one owner at a time. If the function needs to operate on the value, it needs to own it as well. That means that when we try to print x after calling the function, it can't work because x was moved into the function and then dropped when the function's parameter went out of scope. So if we try to compile this, Rust immediately catches our error and tells us exactly what happened. We tried to use a value that had already been moved, and the error message tells us exactly where the value was moved to and which line tried to use it afterwards. We can fix this using borrow. The ampersand is how we borrow x. This creates a reference to x and passes it to the function instead of moving x's value in its entirety. The function's type also changes now to take the borrowed string instead of moving the value like it was doing before. Now, when the function ends, it just drops a reference to x and ends the borrow. X is still owned by its original variable. So that means we can print out the value successfully, and this code works. There are actually two different kinds of references, and the rules about them are how Rust prevents data races. So just a single ampersand is called an immutable reference, and this allows you to borrow some data but not change it. And then the other type of reference is called a mutable reference, and you can use it to change the value however you want. By separating these two cases, Rust allows us to have both flexibility and safety. To see why, let's look at the two rules for references. Well, first, at any given time, you can have either, but not both, of one mutable reference and any number of immutable references. This prevents data races, since those can only occur if you're allowed to both read and write to the same data at the same time. By forcing you to only do one or the other, Rust makes it impossible for you to ever run into this problem, for you to ever have a data race. The second rule is that references must always be valid. That means that if you're borrowing from a variable, that variable can't go out of scope and get dropped before your borrow ends. And this makes it impossible to have dangling references or dangling pointers in Rust. Rust can check for both of these very difficult to debug problems and guarantee that you will never have to deal with them once your program compiles. Let's complete our discussion of the language by briefly touching on two advanced features in Rust's type system. I wanted this to be a practical introduction, so I focused more on the fundamental features of Rust. And in fact, the entire tic-tac-toe application is actually written without really even using either of the features I'm about to discuss. Rust is a productive language that you do not need to learn in its entirety in order to enjoy and be productive in. The advanced features are such that they aren't required, but when you do come to need them, you're really glad that they're there. So the two features that I want to touch on are called generics and traits. And you may have noticed some angle brackets in some of the code that I showed you earlier for option and result. I'm going to explain what that is now. Generics, or generic types, are just a way to write types and functions that can work on a variety of different types. It turns out that a lot of code doesn't really depend so much on the specific types that you provided. So generics help us avoid duplication by allowing us to write a single type or function that can be used on any type that would make sense. Let's look at an example. This function adds two things. The angle brackets are used to declare a generic type t. This says that we want Rust to put in any type that works and use it as the parameters and return type. The problem is that this function won't actually compile in its current form. It turns out that when we said any type, Rust really interpreted that as any type. But not necessarily every type can actually be added. So this is where traits come in handy. A trait is like a collection of methods that we expect a type to implement. And it turns out that there's something called the add trait in the Rust standard library that the compiler uses to figure out how to add two values. So if we put a colon after our declaration of t and specify that we wanted to implement add, we can mostly fix the issue. Because this tells Rust that we don't want just any type. We only want types that can be added. So with that, Rust knows exactly how to add x and y together. That is actually most of what you need to know about generics and traits. Generics allow us to write functions that can take any type, and traits allow us to specify certain things that we want those types to support. So this concludes our whirlwind tour of the Rust programming language. I hope the features I talked about and the syntax I was able to cover piqued your interest and made you want to learn more about the Rust programming language. Once again, I really encourage you to check out the fully commented version of the tic-tac-toe application. It'll teach you a lot more than I could have covered, and it's a complete example of writing a Rust application without any of the advanced features that I just talked about. There's a lot that I didn't cover, which you should definitely go and learn about. Rust has a lot of really nice features to make writing software really easy. And it's a very cool and exciting language that you can actually start to use seriously right now. The Rust book is especially great, and I highly recommend it. I'm also personally working on a free online course to help people learn programming from scratch using Rust. Unlike this talk, the course will have no prerequisite knowledge required. That means that anyone, regardless of background, will be able to learn how to program. It's still in the process of being completed, but you can expect to see some lessons start to appear over the next few weeks. The really unique thing about this course is that it'll teach programming by having you draw pictures instead of getting you to read and write text like most traditional programming courses. It should be a lot of fun for anyone of any age or skill level, so please do check it out. I talk about Rust a lot on Twitter, so if you'd like, you can follow me there. Otherwise, thank you for listening, and I hope you learned something, and I hope you enjoy the rest of our meetup.